Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering. Today, we're covering the biggest compute announcement of the year. AWS just doubled the core count on their flagship ARM processors, and the numbers are making even the most committed x86 shops take notice. 192 cores in a single socket. Let that sink in.
Wait, 192? The previous generation topped out at 96. That's not an incremental improvement.
It's not. And the cache story is even more dramatic. 5 times the L3 cache compared to Graviton 4. That's 180 megabytes of L3 cache in a single processor. To put that in perspective, that's enough cache to hold entire database working sets that would normally require memory access.
Before we dig into the architecture, let's run through today's news. We've got 3 stories that set up this theme nicely.
First up, the new Stack published a piece titled, "In 2026, AI is merging with platform engineering. Are you ready?" The thesis is that AI-driven automation is becoming embedded in every layer of the platform stack. From intelligent resource scheduling to predictive scaling, AI isn't a separate tool anymore. It's becoming infrastructure.
That connects to today's topic. When you're running AI inference workloads at scale, the underlying compute architecture matters enormously. The cache sizes, the memory bandwidth, the core counts, these aren't abstract specs anymore. They directly impact your AI serving costs.
Exactly. And speaking of industry shifts, the State of Platform Engineering 2026 report just dropped. The headline finding is what they're calling the shift down. Platform engineering practices that were previously only accessible to large enterprises are now reaching mid-market companies. Salaries remain strong, maturity is increasing across the industry, and the tools are getting more accessible.
That democratization theme is everywhere right now. What used to require a dedicated team of specialists is becoming table stakes.
Third story, Greg Crow-Hartman published a detailed post on Linux kernel security work. He covers the ongoing efforts to harden the kernel, the role of formal verification in critical subsystems, and how the security model is evolving. It's a reminder that the lowest layers of the stack are getting serious attention.
That's relevant because we're going to talk about AWS's formal verification work on Graviton 5 isolation. It's not just cloud providers doing this. The entire industry is moving toward provable security guarantees. All right, those news items actually set up today's topic perfectly. ARM used to be the budget alternative. Now it's becoming the performance leader. Let's get into the Graviton 5 details, and I want to really understand what's happening under the hood here.
Let's start with the fundamentals of why ARM is different. At the core, ARM uses RISC architecture, which stands for Reduced Instruction Set Computing. x86 uses CISC, Complex Instruction Set Computing. The practical difference is that ARM processors have simpler instructions that each do less work, but execute faster. x86 has complex instructions that can do more per instruction, but require more transistors to decode.
Why does that matter for cloud workloads?
2 reasons. First, simpler instructions means simpler execution pipelines, which means you can pack more cores onto the same die. Second, simpler decode logic uses less power per instruction. When you're running millions of instances, that power efficiency compounds into massive operational savings. AWS doesn't publish exact figures, but industry estimates suggest Graviton processors use 30 to 40% less power than equivalent x86 for similar workloads.
Now let's talk about the M9G instances specifically. What are the key specs?
The M9G instances are available in preview now. These are general-purpose instances running on the new Graviton 5, 192 cores per socket, which is double the Graviton 4. L3 cache is 5.3 times larger than the previous generation, at 180 megabytes total. That translates to 2.67 times more cache per core. They've also achieved 33% lower inter-core latency compared to Graviton 4.
Let's unpack the cache hierarchy because I think a lot of engineers don't fully appreciate why cache matters so much.
Great point. Modern processors have 3 levels of cache. L1 cache is the smallest and fastest, typically a few hundred kilobytes per core, with access times around 1 to 2 nanoseconds. L2 cache is larger, usually between half a megabyte to 2 megabytes per core, with access times around 5 to 10 nanoseconds. L3 cache is shared across all cores, and on Graviton 5, that's now 180 megabytes total.
And main memory access.
Main memory access is around 50 to 100 nanoseconds, so when your code or data is in L3 cache instead of main memory, you're looking at 5 to 10 times faster access. For database workloads, analytics, or any workload with predictable access patterns, keeping your working set in L3 cache is a massive performance win.
That explains the SAP numbers then. They reported 35 to 60% performance improvements on HANA Cloud OLTP queries.
Exactly. OLTP workloads typically operate on relatively small sets of active data, the most recent transactions, frequently accessed customer records, hot indexes. If that working set fits in 180 megabytes of L3 cache, you're essentially eliminating memory latency for your critical path.
What's driving the massive cache increase? Is it purely the 3-nanometer fabrication?
It's a combination of factors. Yes, 3-nanometer fabrication gives them more transistors per square millimeter, which means more die area available for cache. But there are also architectural decisions at play. AWS chose to allocate that additional transistor budget to cache rather than more cores or higher frequencies. They made a deliberate trade-off that favors cache-sensitive workloads. They also implemented bare die cooling. What's that about?
Traditional processors have a heat spreader, a metal cap on top of the die that distributes heat to the cooler. Bare die cooling removes that intermediary and puts the cooling solution directly on the silicon. This reduces thermal resistance, meaning you can push more power through the chip while staying within temperature limits. It's a technique borrowed from high-end gaming GPUs and high-performance computing.
Now let's talk about the single-socket architecture. You mentioned 33% lower intercore latency. Why does having 192 cores in a single socket matter compared to, say, two 96-core sockets?
This gets into NUMA, non-uniform memory access. In a multi-socket system, each socket has its own memory controllers and local memory. When a core on socket 1 needs data from socket 2's memory, it has to cross the inter-socket link, which adds latency. This creates a situation where memory access times vary depending on which socket owns the memory.
And NUMA-aware applications are supposed to handle this, but
In practice, NUMA awareness is hard to get right. You need to pin processes to specific NUMA nodes, ensure memory allocation is local, and carefully manage cross-socket communication. Many applications don't do this well or at all. Even the Linux kernel's NUMA balancing can introduce overhead as it tries to migrate memory pages to optimal locations.
so a single socket design eliminates NUMA entirely.
Exactly. With 192 cores in a single socket, you have uniform memory access across all cores. The memory latency is the same regardless of which core is accessing which memory address. For practical workloads, this is huge. Containers get scheduled across cores, they communicate through shared memory, they read and write to the same file system caches. When all of that happens within a single NUMA domain, you eliminate an entire class of performance variability.
Let's talk about the intercore communication improvement more specifically. How does data move between cores?
AWS designed a custom on-chip interconnect for Graviton 5. The details aren't fully public, but the general approach is a mesh topology where cores are arranged in a grid and data can flow in multiple directions simultaneously. The 33% latency reduction comes from reducing the average number of hops data needs to traverse to reach any core from any other core.
For practical workloads, what does that translate to?
Think about a Kubernetes node running dozens of containers. Those containers are constantly sharing cache lines, communicating through shared memory, passing messages. When one container writes data that another container needs to read, that data has to propagate across cores through cache coherency protocols. Lower intercore latency means lower tail latency for microservices architectures. It's why Honeycomb reported 20 to 25% lower P99 latency on their ingest workload.
Now I want to dig into the security angle. You mentioned something called the Nitro Isolation Engine with formal verification. This sounds important, but also potentially buzzwordy. What's actually happening here?
This is genuinely innovative and worth understanding. Formal verification is a mathematical technique where you prove that software or hardware behaves according to a specification. Unlike testing, which can only show the presence of bugs, formal verification can prove the absence of certain classes of bugs.
Give me a concrete example.
Let's say you want to prove that customer A's virtual machine cannot read customer B's memory. In traditional testing, you'd write tests that try various attack vectors, check that they fail, and hope you covered all the cases. With formal verification, you model the isolation boundaries mathematically and prove that no sequence of operations, no matter how creative, can violate the isolation property.
How does AWS implement this?
The Nitro Isolation Engine is a dedicated component that enforces workload isolation at the hardware level. AWS has used formal methods, likely tools like TLA Plus or COC or similar proof assistants, to model the isolation boundaries. They've then proven mathematically that the implementation matches the model and that the model satisfies the isolation properties.
They mentioned making the proofs available for customer review.
Yes, AWS is providing both the implementation and the mathematical proofs for customers to audit. This is transparency through mathematics rather than just "trust me, we tested it." For customers in regulated industries or with strict security requirements, this is a differentiator. You can have your security team review the actual proofs.
Are Intel or AMD doing anything comparable?
Not to this level. Intel has SGX, which provides hardware enclaves, but that's a different approach and has had well-publicized side-channel vulnerabilities. AMD has SEV for encrypted virtual machines, but neither has published formal verification proofs of their isolation mechanisms. AWS is raising the bar here. The security story goes beyond formal verification, too. Graviton5 includes always-on memory encryption, which means all data in memory is encrypted at rest without any performance penalty. Each vCPU gets dedicated cache slices to prevent cache-based side-channel attacks, and they've added pointer authentication, which helps prevent certain classes of memory corruption exploits.
All right, let's shift to the platform engineering implications. What should teams actually do with this information?
First, let's establish the baseline. This isn't experimental technology anymore. Over 50% of new AWS CPU capacity uses Graviton. During Prime Day, 40% of EC2 compute for Amazon.com ran on Graviton. 98% of the top 1,000 EC2 customers, including Adobe, Airbnb, Atlassian, Epic Games, Pinterest, SAP, Siemens, Snowflake, and Synopsys, have already adopted Graviton in production.
So, ARM is mainstream for cloud workloads, but how do you evaluate whether your specific workload should migrate?
I'd use a four-question framework. First, what's your workload composition? Container-native applications typically migrate with zero code changes. If you're running Docker images, you just need multi-arch builds. The container runtime handles the architecture difference transparently.
How do you actually build multi-arch images?
Docker build X makes this straightforward. You run docker build X create with the --use flag to create a multi-platform builder. Then docker build X build with --platform Linux /ARM64, Linux /AMD64. This builds both architectures and can push them as a single manifest to your registry. When a Graviton instance pulls the image, it automatically gets the ARM version.
What about GitHub Actions?
GitHub Actions supports ARM runners natively now. You can add runs on Ubuntu latest-ARM64 to your workflow. For existing x86 workflows, you can use QEMU emulation for ARM builds, though it's slower. The better approach is to run separate jobs for each architecture and use Docker manifest to combine them.
What's the second question in your framework?
Audit your dependency tree for architecture-specific code. The most common issues are legacy cryptographic libraries that use x86-specific assembly for optimization, some media encoding codecs like older versions of FFmpeg, and older machine learning frameworks with x86-only SIM optimizations.
How do you actually identify these dependencies?
Start with a build. Run your build on an ARM system, either a Graviton instance or an Apple Silicon Mac, which is also ARM. Any dependency that fails to compile or throws architecture-related errors is a candidate for investigation. For runtime issues, look for SIG-ILL, illegal instruction signals, which indicate x86-specific machine code being executed on ARM.
What's the testing strategy? Question 3.
Start with stateless services. They're the easiest to test and the easiest to roll back if something goes wrong. Run shadow traffic on Graviton instances alongside your existing x86 fleet. This means duplicating production traffic to the Graviton instances, but discarding their responses. You can compare latency distributions, error rates, and resource utilization without risking production impact.
What metrics should you compare?
Latency distributions, not just averages. Look at P50, P95, P99, and P999. The average might look fine, while tail latency is worse, which often indicates cache effects or memory access pattern differences. Compare CPU utilization at similar request rates. Look at memory bandwidth consumption, and critically, look at error rates and error types.
Fourth question.
Economics. Instance pricing for Graviton is typically 20 to 30% lower than equivalent x86 instances, but you need to consider the full picture. If Honeycomb sees 15% less CPU utilization on top of the pricing difference, the effective cost reduction could be 40% or more. However, you need to factor in migration effort.
What does migration effort actually look like?
For teams with mature multi-arc CI/CD pipelines, migration effort is minimal. You're essentially flipping a configuration flag. For teams building exclusively for x86, there's work to set up cross-compilation, update build pipelines, potentially investigate dependency issues. A realistic estimate is 1 to 4 weeks of engineering time, depending on codebase complexity.
Let's talk about what can go wrong. What are the common migration failure modes?
The most common issue is floating point precision differences. ARM and x86 have slightly different floating point implementations. For most applications, this doesn't matter, but if you're doing bit-exact comparisons of floating point results, you'll see failures. The fix is usually to use epsilon-based comparisons rather than exact equality.
What else?
Memory ordering. ARM has a weaker memory model than x86. Code that accidentally relies on x86's stronger memory ordering might have race conditions on ARM that were hidden on x86. If you're using proper synchronization primitives, mutexes, atomics, memory barriers, you're fine, but code that cuts corners might break.
How do you detect these issues?
Thread Sanitizer and Address Sanitizer are your friends. Run your test suite with sanitizers enabled on both architectures. Race conditions that only manifest on ARM will often be caught by the sanitizer, even on x86, but you might need ARM testing to expose the timing windows.
What about performance regressions?
The most common cause of performance regression on ARM is missing SIM vectorization. Modern x86 code often uses AVX2 or AVX512 vectorization. The ARM equivalent is Neon and SVE. If your critical path is vectorized for x86 but falls back to scalar code on ARM, you'll see regressions. The fix is to either use architecture-agnostic SIM libraries like Google's Highway or ensure your compiler is emitting Neon instructions.
What's the Kubernetes scheduling story?
You need node labels and taints to manage mixed architecture clusters. Label your Graviton nodes with kubernetes.io/arc equals ARM64. Then you can use node selectors or affinity rules in your pod specs to control where workloads run. For migration, you might start with soft preferences that allow ARM scheduling when available, then move to hard requirements once you're confident.
Example configuration?
In your deployment spec, add a node selector with kubernetes.io/arc equals ARM64. For more flexibility, use node affinity with preferred during scheduling, ignored during execution, and weight it appropriately. During migration, you might give ARM a weight of 80 and x86 a weight of 20 to gradually shift traffic.
Let's talk about regional availability. I've heard Graviton instances aren't available everywhere.
That's a legitimate concern. Graviton 4 is not yet available in some major regions, including Singapore. M9G with Graviton 5 is in preview with limited regional availability. If you have hard requirements for specific regions, check availability before planning a migration. AWS typically expands availability within 6 to 12 months of initial launch.
What should teams not do?
Don't migrate everything at once. Start with stateless services, prove out the process, then expand. Don't migrate workloads with heavy x86-specific dependencies unless you have time and expertise to address them. Don't migrate if compute costs are a tiny fraction of your total spend. If you're spending $10,000 a month on compute and $300,000 on databases and third-party services, the migration effort might not be worthwhile.
Don't assume all workloads will see the same improvement. The SAP 60% number is exceptional for cache-sensitive database workloads. CPU-bound batch processing might see different results. GPU workloads aren't applicable, since Graviton is CPU only. And don't forget about testing infrastructure. Your CI pipeline, test runners, and development environments might need updates.
What's the platform team action plan coming out of this episode?
5 items. First, audit your current architecture for ARM readiness. Check your dependency tree, your build pipeline, your container images. Identify anything that explicitly targets x86 or uses architecture-specific optimizations. Second, create a Graviton migration playbook. Document the process for testing, validating, and rolling out ARM workloads. Include rollback procedures and success criteria. Third, set up dual arc CI/CD. Your builds should produce both x86 and ARM images. Configure build acts, update your GitHub Actions or GitLab CI, and ensure your container registry handles multi-arc manifests. Fourth, establish performance baselines. Before migrating anything, measure your current latency distributions, CPU utilization, and memory consumption. You can't claim improvement without a starting point. Fifth, plan for regional constraints. Map your workloads to regions where Graviton instances are available. For global deployments, you might need to keep x86 in some regions while running ARM in others.
If this breakdown helped you evaluate ARM infrastructure for your platform, subscribing helps us know to make more content like this.
The question isn't whether to adopt ARM, it's whether you can afford to wait while your competitors run 192 cores per instance at 20 to 30% lower cost. The performance is better, the security is better, the economics are better. The tipping point wasn't next year, it's now.